good afternoon. Thank you for being here. My name is Rado Stoica, and I'm an application engineer at Simtech. Today, I want to explore with you the topic of fluid solid interaction, or FSI, and how it is implemented and leveraged using LS-Dyna. Whether we are working in automotive, aerospace, biomedical, or consumer product design, if your system involves both motion and flow, then FSI is essential. And as we will see, LS-Dyna provides one of the most powerful platforms to simulate this coupling accurately. As for our agenda, we'll be looking into an introduction to fluid-solid interaction simulation, the Ansys solution for fluid-solid interaction, an example workflow for this kind of simulation. What is a fluid-solid interaction, or FSI? Well, fluid structure interaction refers to the mutual influence between a fluid, gas or liquid, and a solid structure that can deform or move. The fluid applies pressure and force on the solid, and in response, the solid deforms and alters the fluid's flow path. For examples, we may include airbags inflating and pushing against the passenger, heart valves opening under pulsatile flow, and fuel tanks reacting to internal sloshing. In LS-Dyna, FSI is handled through multiple formulations, as for example, AL or arbitrary Lagrangian invariant for mesh based fluids, SPH or smoothed particle hydrodynamics for mesh-free simulations. FSI simulations help predict failure, fatigue, or instability in the real-world applications. Simulating FSI provides several engineering advantages: accuracy, capture true behavior in dynamic nonlinear environments; cost reduction, minimize the number of prototypes; design validation, verify component integrity early in the design phase; optimization, adapt design based on real physics interaction. Applications include sealing and gasket design, water intrusion testing, biomedical flow systems, safety critical components, for example, crash, impact, and fatigue. Fluid solid interactions problems require accurate definition of multiple parameters related to both the fluid and structural domains. These variables influence the accuracy, stability, and realism of the simulation. So, we may look into fluid type and properties, structure material behavior, coupling method, boundary interface conditions, mesh motion, and remeshing strategy. Despite its value, FSI simulations are numerically challenging. Strong coupling can lead to solver instability. Poor boundary setup may result in divergence. Mesh motion or distortion must be carefully managed. So, you will need robust solvers, smart meshing strategies, and the powerful processing capabilities. That's where LS-Dyna stands out. Now, we'll be looking into the Ansys solution for this kind of simulation. Here are shown all the products in our portfolio. As you can see, the variety of products is quite huge, from embedded software to structures and fluids, from electronics to photonics. As for today, we'll be looking only at the structures products. The structures products is not composed only on LS-Dyna. Ansys provides a lot. For the sake of this example, our focus will only be on LS-Dyna. With it, we can achieve lots of different types of simulation, especially the ones that are defined as explicit dynamics. LS-Dyna is a flagship solver in Ansys portfolio, known for its versatility and power. It's a one code strategy because all solvers are integrated in one executable. It has multi-physics methods combining structural, thermal, fluid, electromagnetics, and more. Has scalability, excellent parallel performance, robustness because it is reliable, repeatable, and cross-platform results. With tools like LS-Prepost, LS-Opt, and LS-Task, you can go from setup to analysis to optimization in one ecosystem. LS-Dyna wide adoption and active development community also mean better documentation examples and support, making it sustainable long-term choice for demanding simulations. Here are more examples of LS-Dyna simulations. As for real-world applications, let's briefly look at where LS-Dyna where FSI and LS-Dyna is already delivering results. Automotive, crash tests, airbag inflation, water wading. In aerospace, bird strike ditching simulations. Biomedical, stent expansions, valve dynamics. For defense, underwater shock, blast wave penetration. And for electronics, drop testing and cooling systems. In each case, the common factor is a need to understand how motion and fluid flow interact under extreme conditions. Now, we'll be looking at an example workflow for FSI. Let's now go step by step through the one example on FSI workflow in LS-Dyna. As in any simulation, we must import the geometry. After that, we must carefully define the material properties, as is very important. LS-Dyna is known to have several material cards available, both in LS-Prepost and also in Ansys Workbench LS-Dyna. There, we must include with very much consideration the properties of the fluid and the properties of the solid. Keep in mind that we want to see the deformation of the solid, so we must include different type of failure criterias from the variety that we have from to choose, and also include the correct properties of the fluid. After that comes the preprocess. Here we must define the Lagrangian and Eulerian bodies. Solids usually are Lagrangian, mesh moves with the material. Fluids use Eulerian or AL, arbitrary Lagrangian Eulerian, fixed or deformable mesh, or SPH, that means we'll define it as particles. After that, we must define the coupling method to set the interaction interfaces and use penalty or constraint based methods for load transfer. Then we must apply boundary conditions and loads. As in any simulation, this step is crucial for a correct simulation that corresponds with the physical testing. Here maybe we may be forced to define the following: pressure inlets, velocity boundaries, and so on, and structural supports and other kind of constraints. After that, we should define the mesh motion and remeshing, which is a crucial part of this kind of simulation to achieving the best results possible. After that, we might move, or we must move, to solving the model and monitoring. We must set the appropriate time step and stability controls, and we must always monitor convergence and physical plausibility. And the most important part is the post-processing. For this example workflow, the solution is conditioned by my number of CPUs and by the end time that I inputted in analysis settings. As you can see, I used 14 cores and 0.0002 seconds end time. And with those parameters, the simulation time took 1 hour. This simulation is actually one of the simplest. It basically involves a projectile with a velocity and the recipient filled with a fluid. And still, the simulation took some time. So keep in mind that this is a complex simulation and it's not only based on the simplicity of the geometry. Moving forward, I will showcase the post-processing for my simulation. So here we have the pressure fields. As the simulation begins, we can clearly observe how the fluid exerts pressure on the structure, especially on the initial impact or motion. Here, areas in red or yellow indicate zones of high pressure. We see these forming exactly where the fluid hits or pushes against the structure. This type of output is extremely valuable in design. It tells us where sealing might fail, where valves might deform, or where we need reinforcements. It's also a great diagnostic tool. If unexpected pressure spikes appear, it might indicate a modeling error, sharp geometry, or instability. Moving forward, we'll go to the total velocity field. This shows the fluid overall motion as it responds to the structure and to the boundary conditions. In the animation, we'll notice streamlines of vector that reveal flow direction and intensity. In some areas, you can see fluid acceleration or swirling depending on the structural motion. Why is this kind of plotting useful? It helps identify flow separation, recirculation, or even backflow. It's especially important in biomedical, aerospace, or electronics cooling applications, where fluid flow motion is required. And finally, let's examine the stress response of the solid structure under fluid loading. As you can see in the animation, von Mises stress builds up at the contact interfaces and areas with high deformation. Watch the red zones, usually these are your potential failure areas. This is a direct indicator of mechanical safety. Are we over the yield limit? Are reinforcements needed? Can we optimize the geometry? This coupling of fluid pressure and structural stress is exactly what FSI helps us solve. The beauty of these three outputs, pressure, velocity, and stress, is that together they give us the full picture. Fluid pressure loads the structure. Structure deforms and redirects the fluid. The system evolves dynamically, and we can see it, measure it, and improve it. That's the power of post-processing in simulation, FSI simulation, and it's why LS-Dyna is such a strong for these complex problems. It's such strong for these complex problems. As for conclusions, to wrap it up, we can say FSI simulations are critical to understanding and optimizing real-world design. LS-Dyna offers powerful tools for solving these problems efficiently and accurately. From pre-processing to post-processing, it provides a seamless environment to high-fidelity simulation. Whether you are designing for safety, efficiency, or innovation, FSI with LS-Dyna gives you the insights you need to make smart, data-driven decisions. Thank you for your attention. For any further informations, please contact myself at the email shown on this slide or also to the company's email. Hope you have a nice day. Goodbye.